When transitioning from a 120/240 delta system with a high leg to a 120/208Y system, it's important to consider the voltage compatibility of existing equipment. The primary concern revolves around how the voltage change affects both single-phase and three-phase devices. Let's begin with single-phase equipment. Most two-pole single-phase equipment rated for 240 volts will typically operate without significant issues on a 208-volt supply. The voltage difference represents approximately a 13.3% reduction, calculated as follows: the quantity 240 minus 208 divided by 240, then multiplied by 100. This voltage drop generally falls within the acceptable operational range for most motors and resistive loads. Motors, in particular, are often designed with a tolerance for voltage variations, and a drop of this magnitude is unlikely to cause immediate or catastrophic failure. However, it's important to note that the motor's performance may be slightly affected. For instance, a motor operating at a lower voltage might exhibit a slight reduction in its output power and torque. In most cases, this reduction is minimal and won't significantly impact the functionality of the equipment, especially for general-purpose tools and appliances. Now let's shift our focus to the more critical aspect of three-phase equipment. The situation becomes more complex when dealing with the 230 volts three-phase unit. Three-phase motors are generally more sensitive to voltage variations than their single-phase counterparts. These motors are engineered to operate within a specific voltage range to maintain their rated speed, torque, and overall performance. Operating a three-phase motor on a voltage significantly lower than its rated voltage, such as running a 230 volts motor on a 208 volt supply, can lead to several potential problems. Firstly, reduced power and torque output are common. The motor may struggle to deliver the same level of performance it would on a 230 volt supply. This can manifest as a noticeable decrease in the equipment's ability to perform its intended task, such as reduced cutting power in a sander or decreased pumping capacity in a pump. Secondly, increased current draw is another concern. To compensate for the lower voltage, the motor may draw more current in an attempt to maintain its output power. This increased current can lead to overheating of the motor windings, which can damage the insulation and shorten the motor's lifespan. Overheating can also trigger thermal overload protection devices, causing the motor to trip and shut down frequently. Thirdly, possible motor damage is a significant risk. Prolonged operation on a lower voltage can cause cumulative damage to the motor's windings and insulation. The increased current and heat stress the motor's components, leading to premature failure. In some cases, the motor may experience winding shorts or insulation breakdown, requiring costly repairs or replacement. To mitigate these potential issues, several additional considerations should be taken into account. Firstly, check the equipment documentation. If available, refer to the equipment's user manual or manufacturer's specifications to determine its voltage compatibility. This documentation may provide valuable information about the motor's acceptable voltage range and any recommended adjustments or modifications. Secondly, consult with the equipment supplier. Contacting the supplier or manufacturer of the three-phase unit is highly recommended. They can provide specific guidance on the potential issues associated with operating the motor on a 208 volt supply and suggest appropriate solutions. They may also be able to offer modifications or adjustments that can improve the motor's performance and reliability at the low voltage. Thirdly, consider a step-up transformer. If the three-phase equipment is essential to the operation of the facility and cannot be easily replaced or modified, installing a step-up transformer may be necessary. A step-up transformer increases the voltage from 208 volts to the required 230 volts, providing the motor with its optimal operating voltage. While the transformer adds to the initial cost and requires additional space, it can ensure the reliable and efficient operation of the three-phase equipment. It's important to select the transformer with an appropriate kVA rating to handle the motor's load requirements. The transformer's rating should be at least 125% of the motor's full load amperage multiplied by the voltage divided by 1000 to account for the inrush current during motor starting. In summary, if possible, it is advisable to avoid operating the three-phase equipment on a 208-volt supply without proper evaluation and mitigation. Consulting with a qualified electrician or the equipment manufacturer is crucial to determine the potential risks and possible solutions. A thorough assessment of the equipment's voltage compatibility, load requirements, and operating conditions is essential to ensure safe and reliable operation after the voltage change. In addition to these considerations, it's important to address the impact of the voltage change on other electrical components and systems within the building. Lighting systems, for example, may be affected by the lower voltage. Incandescent lamps may produce less light, while fluorescent and light-emitting diode, or LED, fixtures may experience reduced lifespan or altered color temperature. Electronic devices, such as computers and power supplies, typically have a wide voltage tolerance and should operate without issues on a 208-volt supply. However, it's always a good practice to verify the voltage compatibility of sensitive electronic equipment to avoid potential problems. Furthermore, the electrical panel and wiring should be inspected to ensure they are adequately sized for the new voltage and load conditions. A qualified electrician can perform a load calculation to determine the required amperage and conductor size for each circuit. The National Electrical Code, or NEC, provides guidelines for conductor sizing and overcurrent protection based on the load requirements and voltage rating. During the transition from a 120/240 delta system to a 120/208Y system, it's essential to re-evaluate the grounding and bonding system. The grounding system ensures a safe path for fault currents to return to the source, minimizing the risk of electric shock. The bonding system connects all non-current carrying metal parts to create a low impedance path for fault currents. The NEC specifies the requirements for grounding and bonding systems, including the size and type of grounding conductors, bonding jumpers, and ground electrodes. In a 120/208Y system, the neutral conductor is grounded at the service entrance, providing a reference point for the voltage. The equipment grounding conductor is connected to the neutral conductor at the service entrance and extends to all electrical equipment, providing a path for fault currents to return to the source. The bonding system connects all metal enclosures, conduit, and other non-current carrying metal parts to the equipment grounding conductor, ensuring that they are at the same potential. In the case of the existing 120/240 delta system with the high leg presents a unique challenge. The high leg, also known as the wild leg or stinger leg, has a voltage of approximately 208 volts to ground, which is significantly higher than the 120 volts to ground on the other two phases. This high voltage can pose a safety hazard if not properly identified and handled. The NEC requires that the high leg be permanently marked with an orange color to distinguish it from the other phases. Equipment that is not rated for the high leg voltage should not be connected to it. When transitioning to a 120/208Y system, the high leg is eliminated, which simplifies the wiring and reduces the risk of misconnections. However, it's important to ensure that all existing equipment that was previously connected to the high leg is properly reconnected to the appropriate phases in the new system. In addition to the technical considerations, it's important to communicate the changes to all building occupants and personnel who may be affected by the voltage change. This communication should include information about the potential impact on equipment performance, safety precautions, and any necessary adjustments or modifications. Training may be required for personnel who operate or maintain the affected equipment. Furthermore, it's essential to maintain accurate records of all changes made to the electrical system, including wiring diagrams, equipment specifications, and test results. These records will be valuable for future maintenance, troubleshooting, and modifications. The transition from a 120/240 delta system to a 120/208Y system is a complex undertaking that requires careful planning, execution, and documentation. Engaging a qualified electrician or electrical engineer is highly recommended to ensure that the transition is performed safely and in compliance with all applicable codes and standards. They can assess the existing electrical system, develop a detailed plan for the transition, and oversee the installation and testing of the new system. They can also provide guidance on equipment selection, grounding and bonding, and safety precautions. In summary, the decision to switch from a 120/240 delta system with a high leg to a 120/208Y system involves several factors, including the availability of three-phase power, the utilization of breaker spaces, and the voltage compatibility of existing equipment. While most 240 volts rated single-phase equipment should operate without problems on a 208 volt supply, the 230 volts three-phase equipment may experience performance issues and require a step-up transformer. A thorough assessment of the electrical system and consultation with qualified professionals are essential to ensure a safe and successful transition. Remember to consult the National Electrical Code and all local codes for any electrical work done to ensure it meets the latest safety standards and requirements. Failure to adhere to the NEC and local regulations can lead to fines, safety hazards, and potential liability. Always prioritize safety and consult with qualified professionals when working with electrical systems. The transition from one electrical system to another is not merely a matter of convenience or efficiency, but a matter of safety, reliability, and compliance with established standards. It requires a deep understanding of electrical principles, a meticulous approach to planning and execution, and a commitment to ongoing maintenance and monitoring. By following these guidelines and engaging qualified professionals, you can ensure a smooth and successful transition that meets the needs of your facility while prioritizing the safety and well-being of all occupants. Furthermore, consider the long-term implications of the voltage change on energy consumption and operating costs. While the 208 volt system may offer certain advantages in terms of breaker space utilization and safety, it may also impact the efficiency of certain equipment and systems. For example, some motors may consume more energy at a lower voltage to maintain their output power. Lighting systems may also experience reduced efficiency or shorter lifespan. It's important to evaluate these factors and make informed decisions about equipment upgrades or replacements to optimize energy efficiency and minimize operating costs. Additionally, consider the potential for future expansion or modifications to the electrical system. The 120/208Y system may offer greater flexibility for adding new circuits or equipment compared to the 120/240 delta system with a high leg. However, it's important to plan for future needs and ensure that the electrical system has sufficient capacity to accommodate anticipated growth. This may involve upgrading the service entrance, increasing the size of the electrical panel, or adding new branch circuits. Finally, remember that electrical systems are dynamic and require ongoing maintenance and monitoring to ensure their safe and reliable operation. Regular inspections, testing, and preventive maintenance can help identify potential problems before they escalate into costly repairs or safety hazards. This includes checking for loose connections, damaged wiring, and overloaded circuits. It also involves testing the grounding and bonding system to ensure its effectiveness. By investing in proactive maintenance, you can extend the lifespan of your electrical system, improve its efficiency, and minimize the risk of downtime or accidents. The NEC provides guidelines for electrical maintenance and testing, including recommended intervals and procedures. In conclusion, the decision to transition from a 120/240 delta system with a high leg to a 120/208Y system is a complex and multifaceted one that requires careful consideration of various factors. By thoroughly evaluating the electrical system, consulting with qualified professionals, and following established codes and standards, you can ensure a safe, reliable, and efficient transition that meets the needs of your facility and its occupants.